So this is going to be the first lecture of structure 6. Basically, it's going to be an introductory lecture. The topics we are going to cover in this course are starting with reinforced concrete columns. In this course, we will learn about the introduction of columns and the classification and its applicability and uses. Beside that, we will learn how to design a column and we will learn to check the capacity of a column. Our second topic is going to be the shear walls. Here we'll learn about its details and we will also learn about its uses and its capacity check. Beside that, we'll also learn how to calculate the reinforcement or to design a shear wall. So pre-stressed concrete is going to be our third topic, where we learn we'll learn about its details along with its advantages and disadvantages, uses, etc. We'll learn how to design a pre-stressed concrete beam. Our fourth topic, which is approximate analysis of frames. We know that a building is a summation of huge number of frames. We need to solve this frame in order to solve a structure. So we learn about the basic concepts and the methods adopting which we can solve a frame. We'll also learn a single method, which is a portal method, and we'll learn how to analyze a frame using portal method. Our fifth topic, which is arches, domes, shells and folded plates. We'll learn about these things and its preliminary design to some extent also. And the final topic, earthquake resistant structure, RCC. Here we'll learn the introduction to earthquake resistant RCC structures, which is currently a hot topic. And beside that, we'll learn about some provisions which are mentioned on our BNBC code about earthquake resistant RCCs. So let's begin. Let's see the books which will be required for this course. Actually, I have already compiled the lectures from using these books. Moreover, I will be uploading the soft copy of these books in a particular drive and share it to you. So let's begin with the introduction part. So in order to be an ideal building, a structure or ideal structure, it should always have these four properties, among which the first property is that it must be capable of achieving a state of equilibrium. What is an equilibrium? Equilibrium means the summation of forces will be zero. We will see it on the next slide. Our second property to be a ideal structure is that it must be stable. The third one is a structure must have adequate strength to carry the load or be capable to carry the load. And the fourth one is it must have adequate rigidity. So as we have said earlier, our first property is equilibrium. So what is an equilibrium? Equilibrium, we have already learned this in structure 1, structure 2, and this is our final course, which is structure 6. So I guess every one of you know that what is equilibrium. Here the equilibrium, we know that the equilibrium means the net summation of forces or the net forces will be zero. In equilibrium we have three equations using which we can easily calculate the reactions. These three equations are starting with the summation of horizontal forces, or summation of h is equals to 0. Sometimes we might say that summation of f of x equals to 0 also. Both are correct. The second one is summation of vertical forces, or the net vertical forces must be 0. And the third one is summation of moment, but summation of m is equals to 0. Actually, here is an example of equilibrium state. It's shown here that we can see this example. This bench, there is a bench resting on a huge stone, and in order to maintain equilibrium state with this large stone, here we need to provide several small stones to maintain this equilibrium state. Here is another example. Here here you are asked to solve this example. Suppose a person is sitting on this bench, which is a swinging bench. It's resting upon this support. This person weight is 40 kg, it's mentioned here, and we don't know the weight of this person, so we are asked to calculate the weight of this person to maintain the bench at equilibrium state. So we can see that this person is applying 40 kg here, which is at a distance of 5 meter from the support, and this person is sitting or applying load. Suppose this person, we don't know the weight of this person, so suppose we can consider that this weight is x kg. So this x amount of load is applying at a distance of 3 meter from the support. So in order to maintain an equilibrium state, we need to apply here the summation of moment equals to 0 equation to calculate this weight of this person. So here is the solution given. We know that the summation of moment will be 0, so the moment that is being created by this person is the 40 kg person is 40, which is force into, or weight into distance. The distance is 5, so we can write here 40 into 5, and this moment is being generated clockwise. On the other hand, from the other side of the support, we can see that this x load is being applied by this person, so the moment will be x into 3, and it's being generated anti-clockwise. As this is clockwise and this is anti-clockwise, we have written this moment on the other side of the equal sign. So in total we can write 40 into 5 equals to 3 into x. Is there any other forces? No, there is no other forces, as the weight of the bench has been considered 0, or the bench is weightless. So if we are asked to calculate the weight of this person, which is x, we have considered already. So from this equation we can calculate the value of x, which is 66.67 kg. So in order to maintain an equilibrium state, this person's weight should be 66.67 kg, or we can say in another way, which is the bench was equilibrium. So the bench was equilibrium due to the weight of this 66.67 kg of weight. Moving on to the next slide. Here is an example of practical life. Here is a practical life example. Here we can see an cantilever structure resisting on this support. So actually these dimensions on both sides are not equal. We can see that these have large dimension from this side, and here the dimension is comparatively less. So how it's being supported? It's being supported by the theory of equilibrium. So in order to support this part and this part, we should create this structure in such a way that the summation of moment remains 0, or the net moment remains 0, and the summation of horizontal forces and summation of vertical forces remains 0. Okay, so here is another here is the detailed one. We can see here the cantilever portion. In order to maintain this cantilever portion, enough load should be applied on other side so that it remains in equilibrium state and doesn't fails. Moving on to the next slide, which is about our second property, which is geometric stability. In order to achieve geometrically, or to be a geometrically stable structure, it should have these four characteristics, or it should be able to resist these four things, which are: it should be a structure should be able to resist any types of displacement, it should resist overturning, it should resist from collapsing, and also from buckling. Here we can see wind load. Due to this wind load, this structure will try to bend or deflect or be displaced. So in order to be a ideal structure, it shouldn't displace, or it should have the ability to restrict this displacement. So what we can do in this sense, we know that when a load is being applied, it's being displaced, it will displace on this pattern, and we can see here that tension will develop on this side and compression will develop on this side. So if we can provide here reinforcements, it will act, or it will resist the deflection by carrying on the tensions. Here we can see the example of overturning and collapse. A structure shouldn't have this property. It should resist overturning to be an ideal structure and to serve our purposes. Here's the example of buckling. So it's mainly a column supported on both sides, both ends. So when a load is being applied from this side, it will get compressed. So after getting compressed, at some stages it will start buckling. So in order to be an ideal structure, it shouldn't buckle, it shouldn't be allowed to buckle. We should be careful about this property also. So how can we solve this problem of stability? So here is an example of this solution. We can provide, suppose here if we are asked to build a large steel structure, and in order to resist buckling or displacement, we can provide lateral bracings. These bracings are provided to obtain the geometrical stability. Here is the example also. And for cases of trusses, we know that due to lateral loads, which example should could be wind load or earthquake load, the truss will get laterally displaced. So when we are providing bracings, it will resist the displacement to some extent, and it will serve our purposes also. Now let's come to the types of loads, starting with the dead load, live load, and environmental load. So what is dead load? Dead load, it's actually the self weight, and it is attached with the structure. Live load are not attached with the structure. um, it is movable loads. And the third one is environmental load. In environmental load, we have wind load, we have earthquake load, we have loads due to snow, soil pressure, and temperature. So while designing a structure, we should be careful, or we should know about our building codes, and using the provisions from building codes, we calculate the load which is supposed to be executed or be imposed on our structure, and considering that load or the factorized loads, we design our structure. So here the example of building codes, which is ACI. ACI means American Concrete Institute. This code is being adopted by American Concrete Institute. And second one is BNBC. We know that it means Bangladesh National Building Code. Third one is Indian Standard or IS code, and fourth one is Eurocode. So here's the type of loading. Here we can see that when a load is being applied directly aligned with the axis, it will be called as axial loads. And the second one is all loads are not in same alignments, so it will have axial load along with some due to the loads here, this beam will tend to bend, and for such reasons bending will develop in this beam. And here we can see the incline load, so here also bending will be developed. So when a structural element is being created, we can see here an example also. When this person is stand on this structural element, it will try to bend. Okay, so when it is bending on this shape, it means the bottom fiber will get stretched or get tensed or get expanded, and the top fiber will get squeezed or get compressed. So we can say that due to this type of bending, actually this bending pattern is known as positive bending, and if it bends on this way, it will be called as negative bending. So when a positive bending develops, compression, we can see from here that compression develops in the top fiber and tension develops in the bottom fiber. So in order to carry this tension, what should be the solution? We know that our steel can carry the tension and concrete can carry the tension. Concrete is better for, or concrete is ideal for compression, and steel is ideal or better for tension. So in order to reduce the deflection or maintain the state of equilibrium, or to be capable of carrying this load, we need to provide restrictions or take measure against this tension. So here, as the tension develops in bottom of fiber, we need to provide steel or rebar or steel reinforcement in the bottom portion of the beam. And as we have seen that compression develops in the top fiber, so we haven't provided any steel or reinforcement in the top fiber by upper fiber. We know that concrete is enough capable to carry compressions. So here is the example, here is the thing that I have mentioned earlier, that this type of bending will be called as positive bending, and this type of bending will be called as negative bending. In such positive bendings, compression develops in the top fiber and tension in bottom fiber. That means if you are asked to draw the layout of the reinforcement for positive bending, where will apply the reinforcement? We will surely apply reinforcement in the bottom fiber, as we can see that for positive bending, tension develops in the bottom fiber, and we know that in order to carry this tension we need to provide here reinforcement. And for upper fiber or the top fiber, we don't need to provide reinforcement generally, but if we generally we don't provide reinforcement in the top fiber. For this top fiber, we can see here that compression develops and the concrete is enough to carry this compression. On the contrary, we can see that in negative bending, tension develops in the top fiber and compression in the bottom fiber. So if we are asked to design for negative bending, where do we need to provide that reinforcement? Yes, we need to provide the reinforcement in top fiber.